if for those of you who have been around HAS for a little bit, I think you already know Matt and Erica pretty well. They're some of our newer members, active over the last couple of years, but boy, they're really they've been really active in the last couple of years. Matt and Erica moved to Houston from the Netherlands, and they've been in the Houston area about the last 10 years. Both are PhD mechanical engineers. They both received their PhDs from Eindhoven University of Technology in the Netherlands, and they work in the Houston energy industry. Right from the get-go, when we started noticing Matt and Erica within HAS, they were very involved in trying to learn astrophotography, and what's happened over the last couple of years is that Matt and Erica have actually revitalized our astrophotography SIG, and and that's on the third Thursday of the month, and the meetings are very well organized and very informative. They also do the outreach events at John Paul Landing on the west side of the Houston area, up off of, I think it's off of West Road, if I remember correctly, and also at Kleb Woods Nature Preserve. Their interests include astrophotography and scientific imaging with a focus on spectroscopy. Matt became a member of the American Association of Variable Star Observers recently, and they both have been very active, as I said, in the astrophotography scene within HAS. I happen to be noticed that with all of the bad weather that was going on this spring, Matt was posting images of their backyard, and they had set up a radio telescope. This is awesome. We haven't had anybody actively doing radio astronomy in the in HAS for quite a while, and I asked if they would kindly share with you all what they've been doing, and here we are. So, Matt and Erica, if you want to take it from here, I think looking forward to hearing your presentation.
Absolutely. Thanks a lot. Yeah. So Erica, if you take over. Yep. Thanks a lot for the wonderful introduction, Don. That's awesome. So yeah, kind of a little bit of an odd topic maybe for what we've seen so far, but we wanted to report out on like a real hobby project that turned out into a lot of interesting stuff. So basically, we wanted to talk today about how we are imaging or measuring the Milky Way with this small, ridiculously small and also cheap backyard radio telescope. So we have a lot of interesting stuff to share. So let me get on with it. So yeah, as Don was saying, we started astronomy in 2023 after we saw like a Twitter post from somebody posting a picture of a nebula that she claimed was taken from her backyard. And then after some digging, we decided to attempt that as well. And then we were looking for a dark place. And the dark side of the HAS is like a phenomenal place within reach of Houston that is safe and just a fantastic place to start your experiments. So that's how we got in contact with HAS. And then from there on, we really rolled into the club. So we met a lot of wonderful people and also and they're sharing what they were doing and so forth. So right now we're hosting the astrophotography SIG. And we do the Clapwood outreach. So we host that as well. So we have astronomy and art with star parties and stuff. And yeah, we always refer to ourselves as astro imagers. So we are using our cameras for doing stuff like making pretty pictures, but also spectroscopy or we done like exoplanet transits and that kind of stuff that you can do with the same kind of equipment. So yeah, we had some previous talks about backyard spectroscopy, how you can get started with spectroscopy, and then of course astrophotography. And on the right bottom side, you see a crowd in at Clap Woods. So lots of people interested in astronomy at these outreach events. So pretty cool stuff. So oh yeah, I wanted to one back. So we the way we observe and what we really like is to experience through experiments, right? So some people they really enjoy when a photon hits their eye, and the whole connection with that photon from the universe is a big part of the experience. The way that Eric and I are doing this is by sometimes carrying out like small experiments, and then with these experiments we're learning something and discovering something about the universe, and that's really our passion. So you will see a lot about that in this presentation. So, but what do you do with the 3 months of solid clouds, right? So if you are doing astrophotography, then the first thing that you of course do is to refresh your darks library. Those are calibration frames for your camera, or you reprocess old images. And then we have, of course, our astrophotography shared drive. So it's like over what is it, 19 projects there, gigabytes of information there. So you can mine through images there if you want. Then you start ordering new equipment, and at a certain point you're like, okay, I have all the parts now, but I have no night sky. So what do I do now? So then we decided to host an astro dinner. So we organized like a barbecue get together. And then at a certain point, you just start clicking around the internet and exploring new branches of astronomy. So, um, so we found this YouTube video from a gentleman called Alex Petit, and he's a member of the SARA, that's the Society of Amateur Radio Astronomers, and they have a club, it's an international club, a YouTube channel, and he was talking about how you could build with small means a radio telescope to observe the Milky Way. And Alex goes into a lot of detail on how you can actually tune that telescope to get the best performance. But well, we just wanted to have a go at it and build it ourselves to see what happened. So yeah, so basically today we're going to talk about that whole journey. So well, why backyard radio? We just explained, right? Cloudy nights. We're going to talk about what type of emissions we can observe. And then Erica is going to touch about the data acquisition and the data crunching. And then we talk about the galactic Milky Way rotation curve. And then we close for further questions. If you have any questions, drop them in the chat or just hold onto them for after the presentation. But of course, very welcome, right? So what are we trying to observe, right? So the thing that we're after is this special thing called hydrogen 1 emissions. And if you're doing imaging, you're probably used to H alpha or H beta even, right, as emission from hydrogen. So basically you have a cloud of hydrogen close to a star, and a star is with its radiation is actively exciting the hydrogen, and then the hydrogen is emitting. Well, these are then the Balmer lines, right? So emitting at a very specific frequency. So for example, for visible light, almost visible light, that's 654 nanometers, is then exactly the wavelength of H alpha. And what you do is that you can put like narrowband filters around that frequency. So you only see that frequency, and that's how you image hydrogen clouds, nebula, with astrophotography. But what we're after here is something very different. It's also coming from hydrogen, but it's an emission from hydrogen in a neutral state. So what happens here is that you have hydrogen, and then just out of randomness, out of its ordinary state, without excitation from a star or not bumping into each other, nothing from the outside, this atom independently just decides to spin flip and change its quantum state. And in that spin flip, it emits a photon, and that photon is emitted at a very specific frequency, just as we have seen with H2, and that frequency is 1.4 gigahertz. So that's the equivalent to a wavelength of 21 centimeters. And that is a very, very rare event. So this spin flip only happens for that single atom once in 11 million years. right? So once in 11 million years, an atom in space is just deciding to change its quantum state, emit a photon. So it's a very, very rare event. And up to like the 1940s or so, people thought that this was just a complete insignificant event. Right around the 1940s, people started digging into it, like in the group in the Netherlands of Oort from the Oort cloud, right? So in his group, there was a student, and he actually theorized that this was something that was going to be interesting to observe for astronomical reasons. And for a long while, they thought that this was so rare because an hydrogen atom can flip under other conditions, not emitting this photon, right? If you bump hydrogen atoms together, then they would change their quantum state, but they will not emit this specific 21 centimeter photon. So after a lot of periodical proof and so forth, they figured out that the big difference is that on Earth, hydrogen atoms are very close to each other, so they bump into each other, so you never see this kind of phenomenon. But in space, hydrogen atoms are so very far apart that this is very unlikely that they bump into each other. And so because they are so far apart, this once in 11 million years event is actually able to happen. And because we have so much hydrogen in the universe, then there's actually a relatively high likelihood that you can observe that. And it took until the 60s or so to actually build telescopes to be able to do that. And that's basically what we're after to observe. And the cool thing is that this 21 centimeter is a very long wavelength. So we're very different from visible light. This longer wavelength can just pass through small particles, different than visible light can. So here's a really cool picture from Heather that she took last week in Galveston. Heather is also a member of the HAS, and it's so this is a really nice meteorite, right? Right about there. But what you see here in the Milky Way is that you have all these black dust lanes, basically. And these dust lanes, they block the visible light. So with the visible light, we're only able to see the visible light, but everything that's small dust is blocked for us. Now radio can probe right through that, because with 21 centimeter, your wavelength is just way more robust for these small particles, so it kind of passes around this much easier. So not only that, it's also for like clouds, where you have a small vapor and raindrops. 21 centimeters is able to pass through clouds. And in addition to that, when you look at our atmosphere also has a certain opacity, a certain transparency. For visible light, we know that it is relatively transparent for certain ranges. But then for radio, our atmosphere is completely opaque. So it is there's just nothing in the way for a radio telescope like we're using right now for 21 centimeter when it comes down to the atmosphere. So I could literally use this setup during day, during night, doesn't matter. And also with clouds and even with a little bit of rain, it doesn't matter. So it's a fantastic kind of hobby to pick up when there's no visible light for you available that day. So that's a little bit on the background of that. So data acquisition. Let's talk about the setup that we built, and then we dive into the weeds of what we're going to do with it. So basically, what I built was a dish on a mount that I made with scrap wood, and the dish is a standard product from Amazon, right? It's basically a Wi-Fi mesh dish that you can tune to 1.4 gigahertz. But out of the box, they only sell these tuned at 1.4 gigahertz. Then you need to have some kind of amplifier, which is basically a notch filter, like a band pass filter, that is also tuned around your 1.4 gigahertz frequency, so that you can basically reject all the other radio activity from your neighbors, your Wi-Fi router, and so forth. So that's basically how you amplify the signal. And then you need a capture card to capture the data, and then you can just store it on your laptop and record it on your laptop. And in between, I have like a piece of coax cable, of course. So here are the parts that I used, right? So this is just a dish from Amazon, $100. Then you have this filter, this LNA, low noise amplifier filter, $45, a piece of coax cable. And then in the past, you needed to have this special box for your data acquisition. And this is where you would probably, get a new mortgage on your house because it's expensive, right? But today, you have these things that are called software-defined radio sticks, and they are $33. So all in all, this whole setup is about $250, and that is just incredible. If you compare that, if you just realize that it took us until 1960 to build a setup that could even capture the signals that we're capturing below $250 today. So that's the setup, and we didn't change anything. It's all out of the box, no soldering, whatever, just plug and play. So let's see. So a little bit about the field of view, right? So you have this dish, there's aperture fever in all these hobbies, right? So what do we get with the 1 meter dish? You can calculate the field of view, the beam width, basically, using a small formula showing the wavelength and then the diameter. And as you see, if the diameter is getting bigger, then your field of view is getting smaller. So with our setup, we are limited to 14 degrees of field of view. So here I use the Stellarium app on my phone. I just put in a circle of 14 degrees, and then you can basically just see whenever the Milky Way passes in front of you on the app. So a little bit of understanding there. So it takes about an hour or so, right, to drift. So if you just hold your radio telescope in one position, it takes about an hour for something to enter your field of view and exit your field of view. And then the other thing that I'm going to talk a little bit later about that, I'm basically adjusting my telescope in altitude direction only, and I do that in steps of 10, so that within 14 degrees of field of view, I have a little bit of overlap as I'm taking more samples of the Milky Way. I'm going to get to that in a bit. But you say 14 degrees field of view is humble, but I'm going to show you how powerful this setup is because of some special tricks. So let's see. So basically what I'm doing in my mount, the scrapwood mount that I made, is that I orient my mount only in pure north or pure south, right? And then the only thing that I change is the altitude, so the angle of this telescope as it points to the night sky. And then I'm doing a drift scan, so I let the Earth motion do my work. So over a day, I'm basically recording at that same fixed position the radio signal that enters my telescope. So if you look at it like a right ascension declination chart, then the declination is set by the angle that I choose with my telescope. And in the RA, that's what I get for free. As the Earth rotates, we're going to cycle through RA over a sidereal day. So this is what you call a drift scan setup. So I don't need any go-to, I don't need any tracking. I'm just using basically the Earth as the motor. So then on the data capture side, so when this goes into my laptop, there's a small program that you can download. It's called AirSpy or SDR hash, and it's completely free. And it takes in basically the spectrum. So this is the spectrum of that it measures directly out of my radio telescope. And then there's a small plugin so that you can basically stack and average out all the Fourier transforms that you get. So the cool thing is that over 5 minutes of recording, I can then stack all those frames, and then within 5 minutes, I stack like 250,000 frames. And the profile that you see here is exactly the transfer function from my LNA, for my notch filter, basically. So I can subtract this from the original signal, and what I will remain with is then the signal that I'm trying to measure, the signature of the Milky Way eventually. And that's then exported to a text file. So this is then the raw data that comes in, and this is where the work really starts. So So plotting that text file, just you get the frequency and the intensity. So you can use Excel or MATLAB. It doesn't matter much, but it's pretty cool because this is exactly at the point where we're passing the Milky Way. So you're seeing basically a frequency of everything within inside that 14 degrees field of view. So it's not you do have a single pixel, so to say, of 14 degrees, but instead of measuring just the intensity, you're getting the frequency information of what you're measuring here. So it is not imaging with 1 pixel of 14 degrees. It is actual spectroscopy. And here you see this hydrogen 1 line that we know by first principles needs to be exactly at 21 centimeters. So that's the equivalent of 1.4 gigahertz, right? And we see that there's a shift here. So basically what I'm measuring here is some kind of shift of the hydrogen that is created by the Milky Way, basically. And we see that there's a difference between what I expect and what I actually measure. This small little peak here, that is noise from our Wi-Fi router. So that's called RFI, like radio frequency interference. So this is not created by the Milky Way, but the big blob and also the shoulder here certainly is. And the reason why these peaks are not like exactly lines is because there's turbulence in the Milky Way arms. So you're getting a little bit of smudging out. And you're also observing multiple arms, and they all have a little bit of different velocities and distances compared to each other. And that's why you get a little bit of a broadening of the signal. We can show it a little bit later. So yeah, basically with $250, we made a radio spectroscopy setup to start studying the Milky Way.
All right.
So now the fun starts. Erica, to you.
Yeah. I'll take it from here. Yeah. So now we're going to do some data crunching, and there will be a little bit of math involved, mostly like geometry part, because it's there's a lot of geometry in the Milky Way, a lot of things spinning around, a lot of angles. I try to make it as easy on all of us as possible. So rather than showing all the equations, I made a bunch of videos to kind of demo what's going on. So hopefully that really will capture the story as we're trying to tell it. So for the data crunching, it's basically pre-processing. There are quite a few steps. So of course, organizing the data, we have to work with the intensity, basically that peak that Matt was showing. We have to do some adjustments to that. What we're really trying to do is use the Doppler shift. So as these clouds of hydrogen are moving towards us or moving away from us, that has an impact on the exact frequency that we are that we are recording, and that's a Doppler shift. So that is going to determine basically how relative the motion of all of these things in the Milky Way is. So we are going to first determine the apparent radial velocity. As we are doing this drift scan, the point at where we're looking in the Milky Way is constantly changing because the Earth is moving around. We're always looking at a different point throughout the day. So we have to do some mathematics on the line of sight. And then finally is where we take into account both the movement of the object that we're looking at as well as our own movement, and that's going to determine by the velocity relative to the local standard of rest. So that's our final step. So let's start moving down this process flow. Well, the first step. And I wanted to say, like, I've done everything in MATLAB. There are a few good Python packages available, like AstroPy and things like that. I chose to do it in MATLAB and do a little bit of my own coding because that gave me the possibility to make some more advanced visualizations. So, if you are interested in that, just let me know, and I can probably share some of the code. So let's get started. So first thing that we have to do is organize the data. So Matt captured all the data, put it all on a memory stick, and then gave it to me. And it was not as nicely organized as it is here, but eventually I ended up putting it in a different folder. So the N stands for north. So that's when his azimuth was pointing north. And then the S stands for south when he was pointing south. And then this is the altitude. So this is north 60, north 70, south 30, and so forth. So if you look in one folder, then that is where all of those text files are stored. So for each drift scan, he has about like maybe 200 to 500 of these text files. And then each of these text files, of course, contain the frequency and then the intensity. So yes, you can do this in Excel, but you have to read in all of this data. So some level of automation is definitely preferred. So we've done that. And then if you do that, and then for one folder, so this is the azimuth 180, south, altitude 60. I plotted all of the text files here in this data. So that is there's 300 and something files. And you can see there's one set with a peak over here, and there's one set with a peak over there. But it's still kind of chaotic data. So the first thing that we're going to do is work on here on the intensity. So this is still on a linear scale, and when we want to analyze data, most of the time we'd like to have it on the logarithmic scale, and in this case we convert it to decibel. And then the other thing that we'd like to do is basically align all of these this data, because the sensor is heating up and cooling down during the day, and that basically it impacts the sensitivity of the sensor. So we want to get rid of this temperature drift. So we've done that by first, taking the decibels, the decibels. So that's you take a log and multiply it by 20, and then the other thing that we did is basically we just took one point and made sure that all of these curves went to this point. This is still not like perfect alignment, but it was already way better than what we started with. And throughout this whole experiment, we were not after perfect. We were just getting after, the experiment and the experience of doing something with this data that we gathered. So now you can see really very prominent these two peaks. So one is a red shift and the other one is a blue shift. And you can still see here this peak, which comes from our Wi-Fi router, which is close by. So this is the first step. So second step, we have organized it. We have basically worked on our y-axis. So now the third thing is that we have to work on our x-axis. So basically we have to do something with this frequency, because we're not so much interested in frequencies, but we are interested in velocities. And Matt asked me to explain how the Doppler shift works, and he explained it to me. And as I understood it, if you're looking at a blue curve coming from the left, then if it moves to the right, it will turn into a red curve. Of course, that is not how it works, but I think we'll all kind of understand how it works. If an object moves toward you, it looks a little bit more bluish than it moves away from us. So this is in a nutshell the Doppler shift. And so this works the same with these frequencies that we have analyzed. So we were assuming to receive everything right here at this 21 centimeter wavelength, but in this case the frequency is a little shorter, so the wavelength is longer. So we have to apply this formula where we basically take the frequency that we expect, so from this hydrogen, subtract what we have observed, divide it by what we expect, and then multiply it by the speed by the speed of light, and this will give us the apparent radial velocity. So if I flip back and forward, you can see that when we look at frequency, it means that when the peak has a smaller frequency, then because of this minus sign, it is now on the other side. So it's now on the right side of the axis. So this is the redshift. This means that it's moving away from us, and if the peak would have been on this side, that would have been a blue shift, that it's moving towards us. So we can do that for all of those curves that I showed you, and then line them up in the time as the drift scan progresses. So this is for one sidereal day, so basically going through 360 degrees. And I'll show you here in a little video, like if we're moving here in time, moving forward, so 24 hours, we are seeing that this peak, first it's on it's giving us a a high apparent velocity, so basically moving away from us. And then on the other side, now it's moving towards us. You can see how the peak shifts around the zero of apparent radial velocity. And I can tell you, when we did the first drift scan and we saw this result, we were like, yeah, it's working. This is awesome. We were kind of like happy that that everything lined up how it should be. So and then after this, actually, we have to still do a little bit more processing, but this was our first moment of success. So the fourth part is, what are we actually looking at? So what is our line of sight? So as Matt showed, we are pointing the telescope fixed on an Earth's position for 24 hours. So we're not changing the azimuth, we're not changing the altitude, but because the Earth rotates, every time we're looking at something different. But what are we looking at? And you can see the Milky Way, it's quite complex. You know, there's a lot of geometry to think about. So we first have to understand what are the galactic coordinates. What is basically how we define everything, where everything is in our Milky Way. So this is a top-down view. Here in the center, this is the core of our galaxy. We are here, just right next to the sun, and so if we want to make basically the galactic coordinates, they are with respect to our own position. So with respect here to the sun, and one of the most dominant axes is then pointing towards the galactic center. And I'll make the Milky Way a little bit less visible, because now we can see that this quadrant is we call that the first quadrant. This is the second quadrant, third quadrant, and fourth quadrant. So this is our inner galaxy. We're looking towards our galaxy, and this is our outer galaxy. We're looking outside of our galaxy. And how we are measuring a position is, if we, for example, want to look at this red star, is first of all with this L. So L is the galactic longitude, just how we have lat long on Earth, we also have lat long in space. And this longitude is measured from this central axis, and then it's going counterclockwise. So this would be like approximately maybe 40 degrees longitude. And then we have a second coordinate, and that's, so if this is the plane of our Milky Way, then our latitude is basically how far we are out of the plane. So, and that's B. So if B is positive, we're above the galactic plane, and if B is negative, we are below the galactic plane. So now we know a little bit of how our galactic coordinates work. So let's look at basically this is a very complex, video, but I'll play it a few times. So what you see here is probably what most of all of you know. So this is RA DAC plot with RA minus 12 to 12 going here on the x-axis, and the declination from minus 90 to 90. And as Matt showed, a drift scan basically just stays at a constant declination. So in 24 hours, we're just, you know, making a horizontal line. So this is our galaxy, and this line, and where it is pointing, that is where we're looking into the direction of the galaxy. So we are looking below the galaxy, and now we're looking here in the fourth quadrant, and we're just now up above the galactic plane, and we're just going round and round. And if we now look at the longitude, latitude, so these are the galactic coordinates. So in RA and DAC, this makes this wavy signal. But here in the galactic coordinates, it's the same Milky Way, but it's completely flat. So if we want to plot our same trajectory, now we have to dip through the Milky Way, and now we're below the Milky Way. You can see we're below the Milky Way, and then we're coming up, and we're popping above the Milky Way. And this is how this process continues. So this is how it works. So this is for a south altitude of 60. If we repeat this process, for example, but now north 60, we start with looking at a different plane. So rather than kind of making that round dish that we saw with south 60, if we look at north 60, we're kind of making this cone, because we're looking more towards the North Galactic Pole. And you can also, we're still making one line in RA and DEC, but you can see that the geometry here in our galactic coordinate becomes this this more elliptic shape, and we're barely poking through the Milky Way here. You can see only that for maybe 2 hours. Here we go below, and then here we pop out of it again, and we are above the Milky Way. So I hope, even if this is very complex, this geometry, that it kind of with this video helps a little bit of where we're looking in the Milky Way. So these are all the scans that you can do basically for different combinations of north and south and altitude. And I think these plots are pretty fascinating. And you can see here, I'm kind of swirling it around, how these field of view change. They kind of are like like two-sided cones, and then yeah, so they, if you, and it's very hard to look towards the south. This is because we are, of course, on the northern hemisphere, so we have this observing point where we basically cannot look below our own horizon. So we can look all the way to north, but we cannot look all the way to south. So if you want to image this part of the galaxy, you have to go to the southern hemisphere. All right, so this is all about a line of sight. So I kind of hit all of the math, but kind of demoed it in terms of these little videos. So now we're on to the last part. So here for this, we assumed that we calculated the apparent velocity, so something else was moving, right? The car was moving. But in this last step, we're also going to take into account that we as observers, as sitting on this earth, are also moving. And you can think about, like, we have this girl walking forward and this boy walking backward. If they both would look at the same mountain, then this girl, as she was looking at the mountain, would see the mountain a little bluish, and this boy, as he's walking backwards, would see the mountain a little reddish. So that is what we have to take into account as well, because we are moving through space and pretty fast. So this is again the galactic center, and we're going around the galactic center. And here is the sun in our kind of galactic neighborhood with all of our stars around us. And these stars, they also move a little bit relative to each other. So it takes a very long time to go all the way around. It takes about 250 million years to go all the way around. So if you think about humans being 100 or 300,000 years old, we barely made it 1 degree in this whole circle. So basically, we didn't go around the sun, around the galactic center even once. But we are moving relative to the stars around us, and we have to take that into account. So what all is happening? So first of all, the sun has a peculiar motion. We have a motion relative to the stars around us, and that makes it peculiar. And this is a fixed direction, and it's about 18 kilometers per second. Then the other thing that, of course, is happening, we as Earth are circling around the sun. This takes a year, and it's roughly 30 kilometers per second that we're going around the sun. So this is also a significant speed. And then we are spinning around the axis, and if we would sit on the equator, that is roughly 0.5 kilometers per second. So actually the movement of the Earth around its own axis doesn't really change our velocity relative to the standard of rest. What does change, of course, as we saw in the previous slide, is because of this rotation, where we're looking in the galaxy changes quite a bit. So our line of sight is mostly impacted by the Earth's rotation. Our relative speed with respect to the local standard of rest is mostly dominated by our Earth movement around the sun and this peculiar motion. All right. So here again, I kind of simulated what this looks like. This blue line spinning around, that is what we saw in the previous slide. That is our line of sight. This pink line, this is the peculiar motion of the sun. So we are moving in this direction and just cruising along. The galaxy is very big, so we can cruise along with 18 kilometers per second for a very long time and not get anywhere. Then on top of that, kind of superimposed, is the Earth going around the sun. And at this time of the year, we're going in this direction. But I will hold my mouse still, and you can see as the video completes and jumps back and forward, you can see that this this yellow arrow actually moves a little bit, because of course, if we would look at the same arrow in 6 months' time, so half a year later, we would be pointing. We would be pointing in the other direction, because then we have gone all the way around the sun. So then there is one velocity missing, and I have to zoom in all the way here to actually see that. So this is again our velocity around the sun, and then on top of that, this last little vector, that is the Earth going around this axis, and you can see how small that impact is. So if we now sum up all of those velocities, then basically our velocity goes from there to there. And this is our line of sight. So now think again about the boy walking backwards, looking at the red mountain, and the girl walking forward, looking at the blue mountain. So if we have a line of sight in this direction, it looks blue. If we have a line of sight opposing the direction where we're moving, it looks red. So that is why in our line of sight, in this, we have a blue shift, and then it switches over to a red shift. So this is basically in our 24-hour cycle, we have a section where we're going opposite the direction that we're moving. And then we have a section where we are going into the direction that we're moving. That is causing this blue shift. And then it's flipping over into a red shift. So you can see how this mathematics becomes quite complex pretty fast, with all the sines and cosines that you have to work with. So now we can correct the velocity that we got from our primary Doppler effect, and we can correct that for the additional redshift that we get because of our own motion. So we sum up the peculiar motion of the sun, our orbital velocity and observer velocity, and take a dot product or an inner product with the line of sight, and then subtract that from the velocity that we had, and that will give us our velocity with respect to the local standard of rest. So this was, as you remember, a few slides back, we had we had the time axis here, and now I made it into the right ascension. This was our primary drift scan with the apparent radial velocity, and where we had one of the blobs above zero and one of the blobs below zero. So this is when we go through the Milky Way, right? So here we. So now, if I convert this to the velocity for the local standard of rest, you can see that everything is now on one line, and that is exactly what we want. Now, basically, we have taken out our own motion and only are looking at the actual motion of the Milky Way. So now, with the with the data as we pass through the Milky Way, we can actually calculate the speed of parts of the Milky Way. So we finally made it through all of those steps for data pre-processing. So now we move on to some more fun stuff, where we're actually going to look at the galactic rotation curve. And I think I'm going to hand it over to Matt right here.
Yep. Yeah.
Awesome.
So in the beginning, we were just capturing data. Then we had to go through these processing steps. And now we are basically, thanks to Erica's analysis and her math, we're now able to measure the actual speed of things moving in the Milky Way. And one of the key traditional questions is like, how does the speed vary as a function of the radius, as a function of where you are at in the Milky Way? So so based on the starlight that you would see, if you just count like where the most stars are, then you could come up with different models to predict what the speed would be as a function of the radius of the galaxy. So if everything would behave as a solid disk, like a CD or a record, right? I don't know, or DVD, right? It's like a solid disk. Then basically the speed would proportionally increase with as you go further out to the edge of the disk, basically. Another theory is the Kepler model, right? So if everything was based on gravity, then basically you would expect that the speed would reduce as you get further and further away from for example, the sun, right, and the planets and all that, right? So a couple of months ago, Dan Roy made a great talk about the Kepler theory. So that's the typical velocity curve that you see if you look at planets in the solar system as you get further and further away from the sun. So if you look at the number of stars, then you could argue that at the core of the Milky Way, you have a lot of stuff going on. So it would behave like a solid disk. And then as you get further and further away in the Milky Way arms, and you get thinner and thinner, you see less stars, you get less mass. So that would behave as if it was a Keplerian motion. And the superposition of those would be then on the right-hand side, what you would expect. So first it would go up as if it was a solid disk, and then at a certain point it would go down. Now, so that is what you would expect just based on the observable star light. So what we're trying to do now is to figure out how we can use the data, use our speed measurements of the hydrogen gas in the Milky Way arms to map out the velocity and measure the actual velocity of the Milky Way, and then see if this model actually makes any kind of sense. And in order to do that, we're going to use a special trick, because if you realize we're just pointing into a certain direction, we are measuring velocity. So how can we infer both the velocity of the object that is moving and the position of the object that's moving, right? So you need to infer like two variables from one measurement, basically. Now there's a very unique trick that works really well in just the first and the fourth quadrant of the galactic coordinates. So as you're looking from the sun inwards to the galaxy, and that's called the tangent method. And it works as follows. So here we are living in our local center of rest with our neighborhood stars and our little sun and little Earth and so forth here in this corner of the Milky Way. So as Erica was showing, we have a line of sight. So that's like the direction of our telescope. And at this particular point, we're slicing through the dish of the Milky Way. So we are not interested in any kind of out of disk positions. We're just looking at whatever is in the dish of the Milky Way. The assumption below this method is that the velocity behaves in certain rings, and these rings are not elliptical, they're actual rings, right? And then you can do a little bit of a math trick here. If you look from your line of sight, like basically from the Earth, right, to along your line of sight, you're going to cross different circles where you're going to basically be imaging or recording the effect of the Milky Way arms. But as it turns out, is that only at one point, and that's the point where the velocity is tangent, so that means like completely orthogonal to the radius. That's the point where the velocity is really pointing the furthest away from you. And in all the other points, basically the arrows, they're moving away from you in some sense. So if you just measure speed, so the Doppler effect, then basically the only point that is your maximum speed is only defined by this point that is tangent towards that circle that hits your line of sight. So so basically I can look at my spectrum plot, compensated for the Doppler effect, compensated for VLSR, and then I just look at the curve, and I take only the right edge of that redshift, the maximum redshift, and that maximum redshift will be always exactly that point on my line of sight because it has the highest velocity. So you can do some simple math on that. This is then a triangle, right? So that you can infer r, the radius towards that point, because you know from literature your distance to the galactic center, that's 8.5 kiloparsecs. And then with a little bit of extra math, you can figure out like, okay, the velocity that you then that you are measuring at that point, you can derive that from the Vmax, and then our own velocity. So our own velocity around the galactic center is 220 kilometers per second, and then we have R0, and from there we just have a simple formula to determine both R and V from a single measurement around that line of sight. So now going through our data, basically these are all my experiments from the backyard. You see that we are right here, we're crossing that first quadrant of the Milky Way galaxy. Yeah, I got it. Yeah, I will click once more, right? Yeah, there's a box on it. So basically, out of all my experience that I did, the only thing that was actually useful for this analysis was living in this box. So we had a lot of crossings of the Milky Way, exactly in that first quadrant of our galaxy, with the objective, of course, to make these rotational curves. And here you see the Erica's script going through my data to show how we're slicing through the Milky Way in our experiment. So looking at the same box, a little bit zoomed in, right? So basically here you see all our experiments, and every time we took exactly that point as it was crossing the Milky Way. And here you see the curves compensated for via the solar, basically, and then we can basically infer speed of that. So one further, right? So using this formula, one more click, I guess, right? So one more click, yeah, exactly. So here you see for each of those line of sights, those velocity curves, and then I'm picking the points where I have the maximum redshift for each of those individual curves. And we put some uncertainty bounds around that because of our quality of picking and so some data noise. But then basically using the previous formula, we can then derive the velocity and the radius of all these curves. And then I can make a rotational velocity curve of the Milky Way. And here it is. So here you see how we have measured at each of these positions of the Milky Way the actual speed of the hydrogen clouds as a function of how far we are from the galactic center. So on the very right-hand side, so that is 8.5, that's where our sun sits, so where we live. And we're basically now have established the velocity for all these points between us and the galactic center. Now, this doesn't look at all like the curve that I was showing before, what we expected. So yes, it does go up like it is a solid disk, but then at a certain point, this kind of remains flat. And that's a pretty cool thing, because that was discovered also in was it the 40s? Yeah, I'll go through that. So basically, I just, first of all, let's compare this to literature, right? So this is us, and this is what we found from literature. And we are only able to image this until 8.5 kiloparsecs, until our sun's location. But other folks, of course, did more measurements beyond that using other methods. And they also have established that that curve actually stays flat as you continue further from the galactic center. And this is the effect of matter that is not luminous or doesn't have particles. That's what we basically call now dark matter. So we've been able to show that there is dark matter in the Milky Way galaxy with our radio telescope. So a little bit of history of that. So what people think happens is that there is this dark matter beyond the luminous matter that it behaves as if it is matter. And originally, Mr. Zwicky came up with that idea, and then later Vera Rubin did a lot of measurements on other galaxies, not the Milky Way, where she established like the same kind of velocity curves. So this is a thing that holds across the universe. Around most of the galaxies that you see visually, there is a dark matter halo. And what dark matter actually is, it's a placeholder definition. Is basically the stuff that we don't know yet. And it's of course active research right now. But just for us, the coolness of setting up this radio telescope on a cloudy day, and then using all the math together with that, and then being able to show the first signs of dark matter from our backyard, that was a pretty cool experience. So yeah, so that was the end of our presentation. So yeah, is there any questions? Or sorry, do I have a couple of more things? Yeah. Oh yeah. Okay, yeah, I see. So a little bit of commercial break before I go to the questions. So this is Clapwood outreach. So we have the 6th of September special on the moon and the star party. So please join. So even if you don't have telescope, just show up and tell cool stories. It's a great evening always. And then if you're interested to learn more and unite with other star gazers, the HAS Discord is super active. So if you're not on it, I'd highly recommend it. Of course, we have the in-person HAS dark side, right? Our treasure of view in the night sky, very close to Houston. Special interest group, as was just announced, and then soon we'll organize another astro dinner in Spring Creek Barbecue again. So. And then the last one I wanted to mention is coming up, as Chris was showing. There's next week, the 7th, so that's on Thursday, 7 o'clock. There's a meeting from Kids Set about cosmic clocks. So a really interesting dive into all kinds of ways that you can measure age and time in the universe. So really looking forward to that talk as well. And now we get to the questions. Okay. Yeah.
As for me, one quick question, and by the way, this was super interesting. Thanks, guys, for presenting it. But so quick question: as you sweep through the center of the galaxy, could you observe any kind of gravity lensing or anything like that?
Yeah. No, not the resolution is not very high, right? It's just you're just measuring 14 degrees. So that is there. And the other thing is that the uncertainty of what we measure is very big because the model that we use with tangent method assumes that those are all circles. But as you get closer to the Milky Way core, it behaves like a bar. So the uncertainty is blowing up as you're getting really close to the core, in the sense that our analysis is too simplistic. Yeah.
Yeah, sounds good. And a quick follow-up. There is something called the Tully-Fisher relation that was normally used to figure out the speed of the spiral arms and so on. Were you able to compare to that, or did you ever, play with overlay with that or anything like that?
No, I never heard of that relation. Do you know when that was?
Yeah, so it's called Tully, Tully dash Fisher, Fisher, and you should be able to Google that. And it's just a relationship between luminosity of a spiral galaxy and its speed. So it's just
Yeah.
a basic graph, I was just
Yeah. I don't know if I've seen it before. What I've seen before is that in the past they try to look at the stars and how the stars are moving outwards from us and inwards from us. And then they were comparing those two motions to infer the velocity. And that was before Oort came up with this model. So maybe that's around that time. But yeah, I'm gonna look it up for sure. Yeah.
Matt, quick question about the actual equipment. The antenna that you have, it's used for Wi-Fi. Did you do anything to tune the center frequency of that antenna, or was it close enough that you could use it as is?
Yeah, it's an off-the-shelf dish where they changed the feeder, already tuned at 1.4 gigahertz. So it's really like straight away from Amazon, and it is used by hobbyists to do exactly this. So I didn't do any kind of tuning. One of the cool things is that the video that I was mentioning in the beginning from the Sarah Club, they go all the way, right? So they are changing out the feeder, and they're also adding like a Faraday mesh on the background of the telescope, because as it turns out, it's not so much that you need more gain to improve your signal, but you have to isolate your feeder from everything around the telescope. So the trees, the grass, everything that is creating basically noise from the ground, that can be picked up by the feeder is actually a bigger problem than improving the gain. So there are also, for example, people that make Yagis, and really from scrap material. It's just incredible. And they're all finding out that isolation from the background is more important than adding more gain at the front of it. So there's a lot of stuff that you can do to further improve. But as the analysis showed, is you're only using a very small part of your signal, just the maximum redshift. So as long as my signal is just peaking above the noise floor, then I'm sufficient good enough at that point. But yeah.
Okay.
Yeah, absolutely. People go, of course, wild on those things, and they improve things in any hobby.
So some folks are actually using a Yagi type antenna, which is it's basically just a planar array, right?
Yeah, well, the best that I've seen so far by the same gentleman was a dish Yagi. So they have like small dishes.
Oh, okay.
So it's a little bit smarter, extra smart.
Okay,
But,
yeah,
yeah.
because I'm just thinking in terms of amateur radio, that's just a planar, they just using planar, but the signals are a lot higher, so
Yeah. It's remarkable how weak of a signal you're able to pick up, and then also what I really did not expect is that we had so little noise, because I thought with all the Wi-Fi and all the things that people have with security cameras, this would be really hard, but it turns out to be very feasible. Even in suburbia area, you could do this. Yeah.
yeah,
Matt,
I was gonna just add a real quick funny thing, but so no photo bombing by Starlink satellites, right?
That's right. Yeah.
Okay.
No light pollution. So yeah.
Hey, Matt, if I'm not mistaken, the clarity of that frequency is by design over the years. Astronomers have successfully lobbied to keep some of the broadcast opportunities out of that one critical area so that we could continue to look at neutral hydrogen around the universe. And so I was going to ask you guys, okay, that was a really awesome experiment. So what's your next experiment?
Well, we have to wait for more cloudy nights for that one. But I must say, I gotta admit, when I started with astronomy, I thought that radio was kind of a dull thing, because you see the cool pictures from James Webb and Hubble. So your interest when you start with astronomy is initially you see all these cool pictures. But as we started to learn more about radio and what they're doing at the Greenbank Observatory, that is just incredible. It's incredible. And that they're able to use like multiple telescopes around the world and then use the phase difference called interferometry to improve the resolution. And what I've been doing now just on hydrogen, they can do on any kind of molecule. So they are literally scanning the universe for all these different chemical combinations that don't even exist on Earth, and that is mind blowing. So I was just as I was learning more about this, I started to really grow a deep appreciation for like professional radio astronomy, and that is a phenomenal good place in astronomy science, right? And what they're able to do is these with a small upgrade, like I think Sky and Telescope just had it in their magazine this month. They basically upgraded to receivers so that they can receive more frequency ranges with the same hardware equipment. So it's a really good bang for your buck. So yeah, I mean, yeah, definitely something is growing. I don't know what's coming out yet.
Yeah. So have you thought about Edition Columbus and start at the dark sky site and start some interferometry of your own?
Yeah, exactly. Yeah. Erica told me like if you want to build a bigger one, you gotta lobby for the dark side.
Awesome work. Way to go.
Thanks. Yeah.
Hey, Matt, this is Bill Spazzuri. I have a question. I believe I heard Don Selly say at the beginning that you were doing some things at John Paul Landing. If
No.
you are not.
No, no, we're only focusing on the Klepwood right now, and those are only 4 events a year. So yeah, that's what we're focusing on.
I'm sorry, what are the 4 events a year?
Klepwood. It's on Muski, so that's a little bit. It's close to Tombol area. Yeah.
Okay, thank you.
Hey, Matt, Erica, one more thing to mention. It's kind of neat that you guys are making this presentation about how you have validated dark matter discoveries as the Vera Rubin Observatory is starting to come online in Chile, and a nice tribute to her work, actually.
Yeah.
So
Yeah.
kind of amazing you could do that with stuff you ordered off Amazon, though, I have to say.
Yeah, thanks. Yeah, definitely. Yeah.
And I have to comment as well that the equipment is a whole lot less expensive than a typical imaging rig. So, astro imaging rig. So there's that too.
Yeah. Yeah, well, I think the measuring is one piece, but then the analysis that Erica put in, right? That is many people are not able to cross that gap,
Yeah.
but you need to be able to figure all that out. So that's a big deal. Yeah.
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 Are there any more questions for Erica and Matt? All right. Well, thank you all. Thank you very much. That was really, really an amazing presentation that the two of you put together. Especially the graphics, and I happen to know it was a fairly short notice request for you to do that as well, and I appreciate the effort you put into it over that short time. So, thank you very much, and we'll see you next month. We have a presentation from, and I just blanked the astronomer's name, from the Lunar Planetary Institute on the Europa Clipper mission. So look for the announcement on that in a couple of weeks.